The next topic we have to address is the importance of water. Approximately 75 to 85% of a cell by weight is water. So water is the most abundant component of cells, and the extracellular environment is also aqueous. Now, there are some life forms that can survive periods of severe water scarcity, and examples of that are the seeds of plants and the spores of bacteria. But these dehydrated states are all temporary, and the resumption of normal activities always requires rehydration. As you know, water is a polar molecule, and that polarity is responsible for the cohesiveness of water, or the fact that water molecules form extensive networks of hydrogen bonds. The cohesiveness is in turn responsible for the temperature stabilizing effects of water and for its solvent properties. Hydrogen bonds, which are non-covalent bonds, form between different water molecules, specifically between an electropositive hydrogen, which is a hydrogen that has a partial positive charge because it is bonded to an electronegative atom, the oxygen, and a second electronegative atom. In water, there's an extensive hydrogen bonding network, and in liquid water, each water molecule forms hydrogen bonds to approximately 3 other molecules, whereas in ice, molecules form hydrogen bonds to 4 other molecules. And it is this extensive hydrogen bonding network that makes water cohesive. So even though these are non-covalent bonds, so these are weak bonds, because there are so many of them, their combined effect is strong. The cohesiveness of water accounts for the high surface tension of water, which allows certain organisms to walk on water. It's also responsible for the fact that water has a high boiling point, a high specific heat, and a high heat of vaporization. So this means that it takes a lot of heat to raise the temperature of water and a lot of heat to evaporate water. Specific heat refers to the amount of heat that a substance needs to absorb per gram to increase its temperature by 1 degree Celsius. For water, the specific heat and the boiling point are higher than for most other liquids. So it takes a lot of energy to raise the temperature of water. So that means that in cells, because there's so much water, the temperature of the cell remains stable despite the fact that there are all these chemical reactions that are happening which release heat. So the high specific heat of water is what gives it that temperature stabilizing ability. In addition to that, water has a high heat of vaporization. So it takes a lot of heat, a lot of energy to break hydrogen bonds so that the liquid water becomes vapor. Because of this, water can be used as a coolant in organisms. When a person sweats, the heat that is required to evaporate the water is drawn from the body, and as a result, the person feels cooler. The polarity of water also makes it an ideal solvent. Now, at this point, I'm going to discuss something that's going to contradict some of the things you may have learned in other courses. In chemistry, you were probably taught that ionic bonds are very strong, even more so than covalent bonds. And that's true if the bonds are in vacuum, in the absence of water. So this is not true in cells where water is abundant. In the presence of water, ionic bonds are weak. And I'm going to say that again. Water weakens ionic bonds, right? So in the presence of water, ionic bonds are very weak. In cells, the strongest bonds are the covalent bonds, so don't get confused. This is something that students tend to get wrong in exams. If you think about this, it actually makes sense. If you put salt in room temperature water, the salt dissolves. And that's ultimately related to the polarity of water molecules. So the oxygens, which have a partial negative charge, interact with the cation, the sodium, and the hydrogens, which have a partial positive charge, interact with the anion, the chloride. So water molecules form spheres of hydration around each of the ions. Another consequence of the polarity of water is a phenomenon known as the hydrophobic effect. And I'm going to talk about this now briefly and we'll come back to it later. When hydrophobic molecules are placed in water, this disrupts the hydrogen bonding network of water molecules, and those water molecules will basically form cages around each of the hydrophobic molecules. Now, the water here is not interacting with the hydrophobic molecules because these molecules are nonpolar. They cannot form hydrogen bonds with water. In the presence of these water cages, there is a decrease in entropy. And this is something that is thermodynamically unfavorable. The interaction of the hydrophobic molecules in turn results in an increase in entropy because you can see that there are water molecules that are now released into solution. So this increase in entropy that results from that interaction is thermodynamically favorable. Now, these interactions between the hydrophobic molecules, these are not attractions. So the hydrophobic molecules are not attracted to each other. Rather, they interact with each other because this interaction increases the entropy of the surrounding water by allowing the water molecules to be released into solution. And as I mentioned, this is more thermodynamically favorable.